I see the questions are already appearing in the chat box for our expert. So
I see. One small request.
we are,
Okay.
your first lecture made us very curious.
I'm not familiar with quantum sensor which we use to measurement. Please give me some description of physical means for experimental setup used for carrying out the said work in your Session-2 for that quick and easier way to beginning the talk itself. Okay. All right. So, yeah, thanks for your comment. And as I was not also sure how broad the audience is going to be, so I just kept that first talk more on the basics, but also less of application based. And the next talk is going to cover some examples and real more applications. And again, some parts are a little basic, but a few things. For example, you asked about the setup. So you will see some pictures and some results here. All right. So
Okay, sir. Please continue. Yeah.
yeah. So the second set of talk, it's I'm going to go through again work with cesium atoms and show some energy level diagrams, walk through some results from here, and then we'll show some sensing with atomic states. So that's what I'm going to capture. And then the next part is going to be sensing with Rydberg atoms. So I will describe what Rydberg atoms are, and I'll show some examples to work. All right. So again, the recap. So that's we saw the energy diagram of cesium atoms, and there are these hyperfine states, and there is 6S, 6P, and these are the so 6S is the actual ground state atom, and this is like first excitation. But there are a series of energy levels, and I'm going to show that as well in later part. But first, I'm going to show how setup actually looks like and what we are going to like how we work with it in terms of like running an experiment. So again, it's a simple diagram. So this is a vapor cell, laser beam goes on a photodetector. So if you send a laser beam and you can scan the frequency. So the laser beams are tunable, so you can scan the frequency of the laser beam over several hundreds of megahertz. So if you just scan the laser, you would see the absorption because the atoms have certain transitions. So in this case, if the atom matches this transition level, it will show up as little absorption peak. But the absorption line is very broad. You see the scale? It's on the order of like the off width is about 400 megahertz. So it's considered very, very broad in the domain of atomic physics. 400 megahertz will give you basically nothing. What is this? Oh, this is a question about squeezing photon. I think we can discuss about that maybe towards the end of the talk, because here I'm not going to cover the squeezing part, but like after the end of the talk, if we have time, we can discuss about that. All right, so this part, the absorption shows you kind of the general feature, but is it very useful? Not really, because it's very broad. But it is practical because it's a vapor cell, and you don't need to carry a whole big lot of lab experiment setup. So it looks very simple. So it has to be will be very useful, but we need to work on it to make it useful. So the feature that shows the line is so broad, and coming back, the line here, the D2, these are very, very narrow. So they are about like 6 megahertz, but the feature shows so much broadening. That comes from the fact that the atoms inside the vapor cell is moving. They're moving all around. They're moving at speed of several hundreds of meters per second. And then just by using a Doppler effect, each of the atoms is going to see the light as a very shifted frequency. So what we are actually going to seeing here is the broadening caused by Doppler effect, and that's because of the temperature. So this is at room temperature. If you were to cool down the whole system down to close to zero, then you will see much finer transition. So this is the kind of problem working at a room temperature system. So the problem is it's very broad. So then it's again limited for any spectroscopic purposes. So then the question is, can we do something about it? It turns out, yes, there is a technique called, well, Doppler V spectroscopy. So all we need to do is use another laser in the opposite direction. So this is interesting. You can do a little bit of like just basic Doppler shift and use two lasers and see if something, if an atom in the center moving around this way or the other side, how the two lasers are going to address that. Because one laser, one atom, it sees a higher Doppler frequency and the other would see as a lower Doppler shift. So, and the result is phenomenal. Immediately you see a very narrow dip, kind of dip here. And this is the feature that's interesting. We chose a very fine line and we can use that. Although like there is a broad background, but there is like a finer feature. We are moving towards kind of looking into the quantum object from atoms. So now how exactly this thing works is what I'm going to just show quickly. So it's there are like millions of atoms in the vapor cell, and a group of atoms are moving with velocity v, and this is v is not equals 0. So if atoms are moving this way with some velocity, it will see the two laser shifted in opposite Doppler shift. So this laser is very strong, so that creates some kind of depth. It's also called like spectral hole burning. And at the same time, the other laser is going to have a little depth here, but it's barely visible. So yeah, the Doppler free idea is very similar to laser cooling. Yes. In that case, you use a slightly off resonant laser. Yes. Here, the idea is very similar because you use two lasers from the opposite direction. In this case, it's close to that. So when you have two lasers, you would see a depth here because of this laser very strong, so that would kind of create a dip, and the other laser will have a shift at this point. When the laser scans and comes to the center, so you get a dip here, but at the same time you get this beam, so you would have added feature in there. So in the result, as the laser meets there, the center, you will see a stronger peak, whereas these things are not going to be shown away. So the final result is going to look like this. So okay, remember this is flipped around. So this is transmission absorption. So now this is transmission. So it's 1 minus. So just don't get confused. But this is a real measurement with that kind of setup, in which you can see fine peaks, all these peaks that correspond to states from f equal 4 to 5, f equal 4 to 5, and then 4 to 3, so 4 to 3. So these are the allowed states. So you get 4 to 3, 4 to 4, and 4 to 5. And there are something called crossovers that comes as a result of Doppler free spectroscopy. That's why you see 6 peaks, 1, 2, 3, 4, 5, 6. So these are, that's the general kind of idea, and you can make the vapor cell based detection, or like, so this is not yet detection, this is like still the basics of it. So, but you can make it work, make it useful for the next part of the experiment. So, right now, as we saw, there are like 6s, 6p, but then we have n number of states. So the Rydberg state is called uh, it's, uh, it's a state where the atoms are excited to a very high principal quantum number. In this case, like n equals 70 to 100, or it could be, there's no fixed numbers. It can be like even 40 or something and above. So this is the energy line that's starting from cesium S state. This is the P state. That S and P has two lines. P has two lines, but those hyperfines are not shown here. So those are kind of somewhere in that, buried in the details. But S to P, and then you have so this is 6s. This would be 7s, 8s, 9s, and keeps on going. Same way, P states keeps on going, and the energy scales as 1 over n square type. So they come closer and closer. So this is the zoomed in picture of these three around n equals 70 to 100. You can see their spacings are kind of coming closer. So this is the also like basic definition of Rydberg states. If you hear from anyone in talk, it's basically those highly excited atoms, and it's very relevant in cesium because cesium has one electron and it behaves like hydrogen, just like hydrogen has one electron. So you can create these kind of features. Other atoms can also show these kind of features, but they have a bit more complicated design, layout, structure. So, right. So some of the properties of Rydberg atoms. So just for like a hydrogen atom, the energy of NL scales as RH by n square. So that's RH is the Rydberg constant defined here. So mass of whatever object and electron and so on. Same way, hydrogen-like atoms, for example, in this case, cesium, has almost similar looking definition of energy level. So except that you get Z square term in there. So because Z is 1 for hydrogen, it's not shown. But the other part is n minus delta. So the delta, also called as quantum defect, it comes from the fact that hydrogen atom has actually no other electron down there in the lower orbits, whereas any other atoms like cesium or anything else, they have a lot of electrons. So because of that, it's the effective, the n is kind of like, there is a position that, okay, let's modify the n and say it's n minus delta. And delta, the value of delta is typically around 3 or 4 or something. And it's a fractional number. So it's not exactly 3. So it's a number added just to make the equation look reasonable and meaningful. And it works to a good extent. There are nonlinear terms though. Anyway, so then the other set of features are large polarizability. So polarizability is a feature when you apply electric field to a system, then how the polarization of the system changes. So, for example, any dielectric material would kind of align its polarization along the applied field or create a tensor polarizability. And that polarization change is kind of somewhat linear, but may also have different terms. But in the case of Rydberg atoms, because you can put the Rydberg atom in electric field, the atom, because its atom is built of like nucleus, that's a positive charge, and then one electron. Because in the Rydberg atom, the electron is like really high lying, so it's the radius of that is goes like n square. So it would be very, very further away from the core. It's like one atom in the center with all the rest of the electrons. So it has one positive charge, and then the one electron is flying around. It's like the classical picture you can think of. So it is easily polarizable because the electron is very far. It's a very large dipole in a certain way. So if you apply any field from outside, you are going to perturb the state very easily. And that makes this kind of sensors very sensitive. But on the other hand, these sensors are also kind of, again, linked to atomic properties, which means it's SI traceable and all those other interesting features. They're like self-calibrated. You don't need to measure it against anything else. All the properties are well established and well known. You can calculate those, and they remain same everywhere in the world. So all those properties, the universal constants of atom is there. Also, other thing is it has a very long coherence time, meaning um, if you think of, so some of these states like this 6p3 half, it has a very short coherence time. In this case, it's about like few hundreds of nanoseconds. That's not good enough. I mean, we're talking about, and the lifetime, the coherence time in Rydberg states are on the order of tens or hundreds of microseconds. So again, it's a very short time, but it's orders of magnitude larger than these, and that's what it matters. So that's very useful for sensitivity in certain experiments, as the coherence time goes as like 1 over root t. We'll see in next slides. The energy level structure, so you get basically a large number of energy levels. And one of the interesting parts with these energy levels are, so the energy gap here is in the order of well, hundreds of nanometers, which is actually like 300 or so terahertz. But as you go up in upper Rydberg states, the energy level spacing comes close to radio frequency band. So, for example, these states are going to cover frequencies from a few hundreds of megahertz up to a couple of hundred gigahertz. So one atom can capture so many different frequencies, and this is it's important and it's very uh, useful because in the domain of radio frequency detection that is used in radar or radio telescopes or 5G or any mobile communication and many different world with that is very hard or almost impossible to make one detector that would detect all these frequencies. That's remember, this is like a technological advantage, and at the same time, this is calibration free, meaning with one atom or like a vapor cell based system, you can detect many frequencies, all calibrated, everything at the same time. Okay, there is a question here. So, the question I'm reading: Rydberg atoms can measure electric field without needing calibration. Means, what's the role of calibration in this sensing? Where is it useful? Well, so that's the whole property of atoms, that you don't need any kind of calibration. So you don't need a calibration. It's a calibration free type of sensing. So I think in your question, the role of calibration is actually it's free from calibration. So that's just not there. That's just not needed. Okay, so now moving on towards the kind of how we implement the Rydberg atom-based technologies for sensing. And one step before we go to some applications is a term called electromagnetically induced transparency. Okay, there is a question again. So the question is, can entanglement be used to violate causality, or is it always beyond by relativistic constraints? Okay. Okay. So first of all, this is beyond the scope of this talk, but no, the causality does not break, and can discuss after the end of this talk. I think that's not on the main topic. So okay, back to the topic. So the EIT is the transparency that is created in an absorption. So if you see the blue dotted line, it's when you scan the laser that on the lower ground state. So forget about this one for a moment. If you just scan the laser, then you will see a clear absorption. And if you have another laser that addresses a Rydberg transition, that opens a window, a transparency window, and that's why it's called transparency. And because it's electromagnetic field, that's the other laser causes it, so it's called the EIT. That's a key technical step that's required for testing the radio frequency fields. Okay, there's a question. As the transitions are fingerprints of two states between them, and this type of MSMT was Doppler free, it mean calibration would not be necessary as it's free of any shifts. Okay, yeah. It's a comment. Local and non-local aspects. Okay, moving on to the next slide. So this is pretty much a kind of a sketch of um, the Rydberg atom-based sensor technology. So you have a RF source. So it's called like a horn antenna. You apply some RF to it. It emits the RF. There is a vapor cell, and there are lasers. So this is called probe laser. So in this picture, the probe is the lower transition line. Again, these are technical terms and very commonly used in the field, but don't get confused. And then there is a coupling laser. So that's this one, which it couples and changes the transparency. So you have these two lasers in there. So they actually look green, and one is infrared, 852 nanometer. You won't see by eye unless it's very bright. But yeah, the other looks very bright green. So you have this kind of configuration, and you look at the signal on the probe laser. So that's the general setup. This part just showing you the cesium atoms with possible different transitions and capturing different kind of frequency. So again, another overview of the setup. So simpler picture: RF source, the antenna, the vapor cell. It detect the probe laser on a detector, and then here is the other sketch where we had the previous case that was called EIT, but now we added this other field, the RF field, because there are different transitions in the Rydberg states, and they can be coupled or addressed by the RF field. So this is the sensing part of that RF. So without this RF, you would just see a single peak like this. So as we were seeing, the blue dotted line. Sorry. Oh, this is okay. A little confusion here. So this is a absorption plot, and what is being plotted is transmission. So it's you subtract one minus the other, and then you would just get a single peak. So that's what this shows here, so a single peak. But when you apply the radio frequency, what that does to this state, this splits into two, and that shows you two peaks. And that's very interesting. Okay, there's one question. How strong are weak detections? Strong or weak detection. Can you explain the notation ND, NS, and NPN? Okay, yeah, I see. So the weak data, I think they're referring to the previous talk. So they're useful. So the how strong are weak detection? I mean, they're used for improvement of some signal, and they work. So it is useful. Okay, the question was about ND, NS terminologies. So yeah, here it's let me just go back to even this plot here. So normally we say like principal quantum number, then the angular quantum number. So those are represented by S, and then there is this half. That's the associated spin. We have 3 half, 1/2, 1/2. So that's what the nomenclature generally says. So that's how you describe their spin in that. Okay. All right. So that's that's these structures. And NDNS is basically N is very large number, like could be 60, 70, or S is also similar. So it's NDNS basically means once you are so this is NS 6S state, and this is 6P. From 6P, due to certain selection rules governed by quantum mechanics, you can only go this way or this way. So this side is all the S states, and this side all the D states. So that's what this NDNS basically means. So this is the basics of the quantum sensing with or RF sensing with the Rydberg atoms. ND and P is again from those D or S states. You can go to P or F states. Once you're in the in here D, you can go to P, or from S to P, and D to P or F. F is not shown in the picture, but that's the general condition rules. Okay. Right. So then so one of the things with these RF fields and its sensing with the Rydberg atoms is the lines, the peaks here, the splitting of that is proportional to the applied field, and that's what we're going to see here. So there's an example of those peaks. Oh, by the way, those splittings are called Outler-Town splitting. So it's another term named after these two guys. So what they observed is like when you apply these RF field, I mean, they used it in different domain, but it works in many of these similar looking atomic field domain. So when you apply RF field, the line is split into two peaks. So it's shown here in the kind of these two blue lines. And the splitting, if you measure that and you plot that against the applied RF field strength, so the field of this radio frequency, it shows a very linear relationship. So that's the kind of the calibration part of it, and also it captures a very wide range of frequency. So you actually you're building a device that can detect radio frequency field. It can detect DC field as well, but I'm just showing you radio frequency field in this set of slides. Also because it's more challenging and more technically useful task to detect radio frequency over a wide range of frequencies. So that's what this part shows. And the sensitivity of the sensor, depends on, like, this is a general term, though it's not specific to just to this, but any sensor for that matter. So you apply a field, like represented by V, and the E is the change in energy level. So in this case, the splitting is, and V is the field that you're applying. In this case, the field. And Q is some kind of dependency, so it can be 1 or 2 or some other numbers. But here it's going to be 1 because it's linear relation. So the splitting and the field is like sloped as 1. And the important part also comes in the sensitivity is the square root of coherence time. So longer it is, the better your sensitivity would be. And as I said about the Rydberg atoms, they are long and they're useful. All right, so what can this be used for? Like, so now on, I think there'll be more pictures and more real examples. So one of such examples is actually my workplace, where what we work on is have a whole rack, this kind of a small table or kind of a trolley mounted laser system with some processing system, and you can run software on it and do the processing and get the results out. On the on the experiment side, so this kind of box looking and the spokey look design, basically it's called an echoic chamber. So it's like an echoic, meaning there's no echo of radio frequency. It's a special kind of chamber where there is like when you send RF, it does not bounce back. So it's a place for testing and characterizing devices. And the device could be an antenna or various, mainly antenna, but various kinds of different RF sources that you can place in there. And you put the sensor, which is vapor cell based. So it's a purely glass dielectric. So that's what you can use to kind of detect the field inside and obtain some information. So it has the advantages of these kind of sensors. It's a non-metallic RF detection system. So normally, most of the sensors are based on some sort of metal, like an antenna is a sensor as well, but antenna is purely metallic. And if you bring an antenna close to another antenna, what you're going to detect the field of, the amount of distortion that sensing antenna could create is that you're not going to detect the bright field. So then it would just be kind of useless for detecting because you have too much of disturbance. There are techniques people use, and it's very cumbersome, that they use multiple set of antennas to calibrate one or the other and then do some kind of calculation. It's a whole lot of complicated process. But again, those antennas are just going to work for one set of frequencies. It won't capture the whole range. So that's, and if you're changing the frequency, you have to recalibrate everything again. Okay. The other thing about these glass vapor cells are they have very low cross section. So the cells actually look like this kind. So it's a tiny glass cap kind of envelope with cesium atoms in it and some fibers that carry the light, and it's kind of attached to it. It's glued in certain way. There's no metal and everything is fixed. And so they have very low cross section. So basically, it does not scatter any RF that you're going to detect. You can also go very close to the RF detection source. So like if you're detecting radio frequency on different kind of devices, you can go like really, really close. And then it's again, it's repeating, it's all optical detection. So there is no electronic component. And that's very important because it's a electromagnetic pulse attacks. So when you have a very sensitive radar or such radio sensing technology, what the what people can do, or like some war kind of situation, what can be done to damage those, because those sensors are very sensitive, the ones that are used in current classical technology. They're very sensitive electronics. But then if you apply very high pulse of electromagnetic field, that can just go through the sensor and go through the chip and just damage the chip, and it won't work. That's one of the kind of damaging trade-off with uh, the the existing classical sensors. But the RF based sensor is like purely optical. There is like no wire between this part and this part. It's all fiber. There is no electrical signals at all. So that makes it like prone to such kind of attacks. And again, it's a very easy to test the field, because you just tune a different Rydberg state by just changing the laser's frequency, and then you're set to test different frequency band. Okay, some other examples here. So this is from some research work. So this is a waveguide. So it's like a copper plate with a tiny wire, like it's a etched waveguide. So you can apply some radio frequency from one side, and this will just guide through to the other side. And this waveguide contains the frequency inside, the signal inside. And one of the, just as a technology demonstrator, you can use these kind of sensors to detect the signal just above the surface. And this shows the result as like crossed around across this point. And then you see the signal is higher, lower, higher, lower. This kind of measurement is close to impossible with any classical testing technology, because, well, the classical technologies are okay. So one other feature of the Rydberg-based sensors are, because you're detecting optically, so your laser, so your detection volume can be as low as few millimeter or even less than that, and that's remarkable, because in radio frequency, if you're detecting, let's say, a few gigahertz frequency band, your wavelength is very, very large. It's like several centimeters. So such a small, tiny system, you can resolve the radio frequency field across this chip. See, the dimensions are like very small. You can actually see a lot of fine structure informations around there. It's also a field in kind of detecting. So this is a simple setup, but if you're designing kind of a big complicated RF circuit or RF board, which has radio frequency going on the circuit board, and you don't want any leakage or any hotspot or anything, you can detect by these kind of technology very close to the surface and find out where the problem is. Okay, there's just another example of such radio frequency sensors. You can not just only detect the field, but also detect the phase of the radio frequency. So in this example, the vapor cell has two laser beams. You can see two beams here. And the both are being detected on two different detectors. Yeah. So red line is the detecting beam. The green line is the one which causes the Rydberg excitation. So now you have basically two planes, 2 points. So just showing a top view, you have these 2 points where you're detecting. There's an RF coming from this side. You have an angle of that RF. The RF would first arrive here and later here. So in this test, you can see that there is the two RFs are arriving at different sites. Or it's a little wrong label. Location 3. But the point is, you can detect the arrival delay between the other. Okay, the other part of characterization of such radio frequency sensors is like the usual sensor based on those antenna. They are very polarization sensitive, meaning if the polarization is flipped around, you won't be able to detect. You have to use multiple antenna system. Here, it's the polarization can be detected on like all different possible different angles with little to no distortion, and it all depends on different atomic sublevels and transitions. So you can use lasers properties to address different sorts of polarization. It's just a demonstration for two different frequencies. This example just shows a frequency RF field mapping around some surface. You can take the sensor, move it around close to any surface, and you get some field pattern. And just to show you a bigger picture, so you have an antenna, you can map the field very close at some distance, further distance, and there are different interesting zone of range where the field patterns are very different. In a traditional measurement system, it's close to impossible to detect very close to the RF source. With the Rydberg sensors, you can detect everywhere and find out the full profile of the RF field. So yeah, with that, we've come to, I hope I've given some examples and showed some real applications of Rydberg sensors. And this is the summary. So showed you the energy level, the various different spectroscopic techniques, and all the applications of Rydberg atom for RF sensors. So there's a question: what is the relationship between vapor cell and detector? Oh, so the vapor cell is, let me go back here. So this is a vapor cell that contains the atoms in it, those cesium atoms. And the detector is what detects the light when it passes through the vapor cell. So you're going to expose the probe, the laser is going through the vapor cell. That's the, and this, the detector is just the light detector. It's not detecting the radio frequency. The radio frequency is being detected by the atoms. The light is only addressing those atoms. That's the answer. More questions?
Thank you, sir. Most of questions you have already answered during your talk. So it was a very nice talk, and I hope participants have enjoyed it. And there are so many queries that you have already responded them.
Yeah.
So participants, if you have any further query, please send write in the chat box.
Mhm.
And if you think like most of things already discussed, then we should close the session now, because we have another session today that is from 2 to 4. And I
It was
request
about the previous talk, and just going through that. Exact. No.
the quiz is already open, so please try to submit by tomorrow. I request Dr. Norman,
No,
please,
I think I've
if
answered
possible.
that. Yeah.
Yeah, okay.
Yeah. Okay. There was one question that